Cool. Good to go.
Just tell you. Thanks for this.
So, when you have money, message get lines, your legs, tracks. So there's 20 minutes. So the first one is the second one. It's like a podium track one.
So, two months. Lunch.
Yeah. What's that? Hi. Good morning, everybody. Thank you so much for sitting down with me. Today I'll be covering some of the work that we did in partnership with one of our sponsors, another one of the sponsors here, studying the ways we can mitigate the risk presented to a rocket by vibrations. So we can begin by understanding what conditions are potentially. And that is back and forth oscillations induced by speeds. There's a couple different factors that influence the size and strength of vibrations on a rocket. For one, the magnitude and direction of forces that I'll discuss later, the frequencies of these forces, the materials of the rocket, the shape and size of the rocket, which both play a big role in determining the natural frequency, which will determine where the rocket was. As I touched on earlier, there's a couple key sources of vibrations in the course of flight. For one, you have the parts of sustainer motor, two-stage. You have the parts of booster motor, and the transfer there. You have air resistance and air forces across the structure, fins, body tube, things of that nature. And of course, gravity as the rocket spins, or the force of gravity changes, and that produces tons of vibrations. And apart from the ground, its destructive force any rocket can face in flight are shocks and vibrations. Getting into the nitty gritty, some of those risk factors that I touched on earlier, some of those vibrations. For one, it can have a huge impact on the performance of electronics, even if it doesn't break anything. They can impact the measurement ability of your sensor suite. They can impact the ability of the sensors on board to record information, particularly MEMS sensors that rely on microscopic movement to create electrical signals. They can damage components, particularly solder joints for the case of avionics systems. Through-hole joints and surface mount joints can both become separated, which would cause big issues for any sort of electronic component. They can cause communication interference when radio systems are separate from computational systems. The vibrations connectors can cause additional electrical interference in the signal line, which degrades signal quality, generating noise, and can cause data loss. Like I said earlier, the vibrations are sort of unavoidable because they're naturally generated for the course of the flight. You can do some things to mitigate the generation of vibrations, but there's really nothing you can do to stop it completely. And from the structural side, strong vibrations can play on material weaknesses, which cause failure in structural components, the breakdown of the rocket. This all establishes a systemic need for testing methodology so you can ensure that your rocket is safe from vibratory risks. So vibration testing in industry is done in a controlled environment where you use known vibration patterns and calibrated equipment to establish how your systems will behave in the field. Testing also shows us how reliable our electronics are under these vibratory circumstances, which is crucial for saving costs during the design process and being efficient with the number of parts that we have. We can also identify weaknesses in the materials and electronics designs. By identifying these weaknesses, we can proactively address them, and we can ensure that the data we collect is more reliable and consistent. And all of these things and testing methodology can help us implement vibration conscious design, which is a proactive approach to addressing potential failure modes that we can attribute to vibrations. So this fits into our team methodology for designing resilient systems. So in this specific case, we proactively were identifying risks where we were able to identify that vibrations pose a potential risk to our avionics systems, and that could affect flight survival and the data quality of what we collect. We developed testing procedures by partnering with industry advisors, such as our sponsors at Lab Controls, specifically a huge thank you to Ryan Lang. We are able to research existing testing methodologies, things that are used in industry to approach this risk, and tailor those methodologies for our specific use case by writing an experimental procedure that targets the risk factors that we want to address. Then we can improve these designs based on the data we collect by performing our experiment, systemically collecting information about how that experiment goes. We have direct insights that we can use to improve our designs. So this is sort of a mathematical description of vibration systems as a system of second order ordinary differential equations. On the left side, we can see the net force on a specific item, which is a combination of the damping coefficient, the natural frequency, and then the existing angular frequency of the system. We can also see that the overall force on the entire system is the sum of the forces on each of the components. Some key terminology as we dive into our experimental procedure. A vibration table is a large mechanical device used to generate the input vibrations through the movement of a magnet in response to an electromagnet. If you've ever used speakers playing music, you'll notice the center membrane vibrating. The way that a vibration table itself works is almost identical to how a speaker works. There's a suspended magnet and an electromagnet. And the response signal responds to the electromagnet. The demand signal, which is the target waveform and energy level that we specify during the vibration programming. Next, we have the three axes of vibration, the transverse, axial, and normal axes. So these are all perpendicular to each other. The axial and normal axes are the axes that are coplanar to whatever surface sample you have. In our case, the PCB, those are the two axes that are in the same direction as the PCB. The transverse axis is the axis that is perpendicular to the PCB, the in and out axis. Next, you have, like I said, the PCB, the printed circuit board, which is a flat board that contains mounting surfaces and traces that help us connect different electrical components together. Normally, they're made out of laminated fiberglass and etched with copper. The surface mount design versus a through-hole design. Surface mount electronics have conductive pads that are mounted to conductive pads on PCB. Through-hole designs are designs that have leads that are passed through a through-hole and then soldered to PCB. They both have, it's important to differentiate because they have different exposure to vibration risk and different axes of vibration on which. The natural frequency, the frequency at which a system will vibrate in absence of a driving damping force. This is most easily expressed as if you smack something, what noise does it make? That's the natural frequency. It's the frequency that it wants to vibrate. Resonance is the phenomenon where you drive the system at its natural frequency, which causes an accumulation of energy, which increases displacement and force applied to the system. So our first experiment, which is studying material damping, was an A-B comparison between PLA, polylactic acid, which is a traditional light-duty filament that has rigid properties, and thermoplastic polyurethane, which is a pliant filament that has rubbery properties instead. The key question we wanted to ask is, can we use materials to build an AV bay that damps shocks and vibrations? And we tried to do that using TPU. Our experimental procedure was mounting our flight electronics along with crystal accelerometers to two different electric PCBs, one mounted on a TPU slide and one mounted on a PLA slide to measure any difference in vibration transfer. These slides were in turn mounted to a rigid body, an ASA body, to ensure that the control was less. We used two different vibration profiles specified by the standard SMC-16, which is a testing standard developed by the United States Air Force and NASA for upper stage launch vehicles. And we did this at the Environmental Stress and Screening Lab at Ground Controls. In particular, we wanted to keep a focus on higher frequencies, as those are more likely to occur on board small aircraft, such as a student rocket. So here we can see our experimental device. This is the TPU sled here, which is slightly rubbery. This is the PLA sled on the back, which is firm. We have our electronics here with our accelerometer here. On the back side, there's a corresponding accelerometer. There's an accelerometer mounted to the test plate to get a control. And there's another accelerometer mounted to the back, say, to give us an understanding about the structures of the. So our first search was a resonance search. And we mainly want to focus on resonances in the transverse axis. That's that in and out axis, up and down. It causes perpendicular motion, so bending and bowing in the PCB. So sort of like a Pringles chip, which is the most destructive force because it'll delaminate the PCB and it'll cause separation in surface boundaries. So we perform a resonance search by sweeping across a large spectrum of frequencies and noting where the measured energy is higher than the input energy. You'll see that it spikes in the curve. As you'll see later, the TPU sample has lower spikes and it has lesser resonances at higher frequencies. So first here we can see the comparison between the three samples. PLA in green, you can see has huge spikes up here. This spike secondarily is caused by a spike in ASA. Both samples vibrate in response to the central structure. But independently, we can see that the pink line, the vibrations for TPU are actually much lower than even the input signal, which is 1G, at these higher frequencies. That gives us an indication that TPU is actually very well suited for damping these higher vibrations, meaning that it might be the right filament to choose for our avionics bay. Our second test, which is randomized vibration, it's a standard stress screening protocol used by these aerospace companies, where you drive a broad spectrum of vibrations into the same system. The probability of each signal's frequency and amplitude are determined by an existing distribution that is set in SMC-16, which is, like I said, a test spec developed by the United States Air Force and NASA for upper stage launch vehicles. Looking at the curve, you'll see that it becomes very clear that TPU does damp vibration transfer into our electrons. We can take a look at PLA first here. These are the three axes in PLA. We can see a similar spike that we saw in the last graph. And we can see that in this upper range especially, which is the focus range for our experiment, the PLA has very high levels of energy transfer, including some very nasty spikes up there where you're having a force that's orders of magnitude higher than even the mass. When we cross compare that to TPU here, we see much lower overall, and we see no spikes in this upper range, which is very good. Side by side, you can see how good of a job the TPU does at damping these randomized vibrations and reducing the energy transfer into our electrons. Our second experiment is a A/B comparison and a survival test between switches. So when we're designing our avionics systems, one of the main focus points is the switch that we choose to use, especially because space is a key constraint, especially if you do a nose cone design where all of your avionics to a nose cone. The more avionics you have, the more space it takes up, so you need switches that are compact. So the two options we chose are both standard in the high power rocketry space. The first switch type was screw switches, which you can buy from a lot of the rocket supply websites. They're extremely compact, which is a huge advantage. And they are designed as a conductive screw that's screwed into a conductive socket. Once the screw reaches a sufficient level of tension within the socket, electrical current flows and your system turns on. The second switch type is the key switch, which is very common around here, which is a traditional key switch, which is much larger but has locking positions, which is really important for our experimental procedure. The reason this is really important is because a switch disconnect in flight due to a high impulse flight event, such as ignition, stage separation, or just general vibration, could cause your avionics to fail because of the power discontinuity, which means you wouldn't have subsequent staging events. So your drogue might come out, but your main wouldn't. You would have a pretty bad time. Like I touched on earlier, these different switches have different mechanical properties simply because they're designed different, which means that they have different exposure to that vibratory risk. And our testing procedure was evaluate by sending shocks and general spread spectrum vibrations, the same distribution as SMC16 earlier, and monitoring if there are any voltage drops. So this is what our experimental procedure looked like. The two switches you should pay attention to here are the screw switch down here and the key switch up here. You can see one of those accelerometers from earlier. Again, just like how we tested the avionics system, it's important to have a control understanding of how the structure itself is vibrating. And you can see electrodes coming out from both of the switches, which we use to send a voltage to and monitor if there were any drops across the switch. If we take a look here, we can see some very interesting results. The screw switch, which is the lower in purple, key switch, which is up above in black. The key switch is a perfect steady constant. Meanwhile, the screw switch, when we apply shocks, has big drops, which would likely cause your electronics to power cycle, meaning that they're not necessarily safe for using on flight critical electronics, right? So if you have significant shocks, like you would under any sort of staging event, you can have shocks up to 100 Gs for very short periods of time. Any flight critical electronic, you should be using key switches for those instead of screw switches. Broadly, just to take away some conclusions, intelligent material component choices can help you build avionic systems that are more resilient to the vibrations and shocks that you experience in flight. Rubbery filaments, fine filaments like TPU, can be used to print avionics bodies that dampen key parts of the vibration spectrum and protect your electronics better. Locking switch types, such as key switches, which are standard, are more resilient to shocks and vibrations, meaning that they're better fit for critical components. And broadly, at a higher level for team philosophy, working with our experienced industry partners can help us understand to ask and also answer novel questions that we would not be able to with test flights alone. I want to thank you so much for sitting in today, and I'll open the floor up for questions.
So you did finish about 2.5 minutes early.
Okay.
So we can add that to our question time.
Sure.
So in 7 minutes.
So that question actually thought you there you go.
Please.
With the vibration, how did that affect your
Absolutely, it did. As I touched on earlier, TPU versus PLA, we found that TPU does dampen vibrations. So our design this year does use TPU for the entire structure of our avionics bay. Likewise, when we did test flights in January and November, we flew screw switches to power our SRI electronics. After doing this testing and seeing that there were huge discontinuities, we moved away from screw switches and we now use key switches for all of our electronics.
I can ask one more question. I can say. So for your material choices, when you were thinking about designing your experiment more in the context of wide range commercial applications, or more in the of this competition?
Mostly in the context of this competition, our design for student markets.
Okay. Did you consider other potential filament mounting materials when you chose to be away?
You mean for the just like the printing of the?
Yes, yes.
I think PLA and TPE were the most practical options for those that. Now, granted, within PLA and TPE, there's a lot of variety. We just chose what TPE we had on hand. But just feeling them, you can tell that they're pretty different generally. So those are chosen because they're cost effective, really not.
Yeah, yeah. I would like to see a design is kind of more for this experiment. I know that I'm not sure about TV, but I know that PLA is not very loose.
Yeah, that's why our central structure is made out of ASA. We just wanted to have an A/B comparison of slides. I think 3D printing is best for style engineering as a team. I think we have a lot of revision cycles where we change how wiring is done, we change the boards that we're flying, just as we learn more and more about different risk factors. So having the flexibility of 3D printing helps us in very quick turnaround between design change and getting it out within 48 hours, drastically different stuff. So I think it's the best for us.
I was wondering about the specifics of this testing. At what point, like how much G load did you have to apply to get the screw switches to disconnect?
Yeah, that's a really great question. I didn't put it down here, but this shot was 10 Gs, this was 15 Gs, and this was
So
25
not
Gs.
really that high.
No, not very good at all.
And do you know what screw switches you tested?
I think we bought them from MissileWorks. I don't recall the exact.
Are those the like little rectangular green boards with the screw?
You can just take a look right here. It's a little black board.
Oh. Okay, gotcha.
That was a great question. One in the back.
Follow-up question, how many trials of these screw switch and key switch tests did you run just to eliminate any sort of like setup error?
We ran one trial with multiple shocks.
I believe you mentioned something about using TP to print the entire avionics bay. Do you still think you could see similar vibration mitigation if you only use TPU for certain parts of the bay or certain aspects instead of using it for the whole bay? Or
yeah, that's a really interesting question. One of the thoughts that we had was using separate pieces because different materials stand different ranges of vibration. But I think due to like manufacturing constraints, it isn't always practical for us to have a multi-part system. It worked for our launches in November and December, but for a spaceport rocket, it was sort of necessary simply due to space constraints to have one material. And because the higher range, which is more destructive and more common in student rockets, is damped by the TPU, we chose to spread the whole thing out of TPU. Yeah.
Do you have can you go to your testing with the two slides?
The two slides? Yeah. Yeah. Yes. So this is ASA, this is TPU, or this?
Okay, so your mounting for your rack is ASA, and then that's attached to.
Threaded rod, steel threaded rod.
Have you considered any sort of vibration mitigation in the physical mounting that's connected to this? I know that the TPU and the ASA will kind of.
You mean between the threaded rod and the ASA?
Yes, just kind of because that's like that would be cutting it off more closer to.
Yeah, I'm not sure. I think one of the immediate constraints would be its manufacturing simplicity.
Yeah.
The turnaround for this has to be pretty quick. It has to be evaluated the design. So any sort of degree that adds complexity is a challenge. I think mitigating near the boards themselves is a viable strategy, simply because we don't really worry too much about the structure itself falling apart. If this was a concern where the structure might fracture or delaminate, we would probably address it closer to the thread rod. But since the main concern is delamination of electronics and signal integrity, we're comfortable addressing the vibrations closer to this.
Any other questions?
Or you mentioned something about the wire, JLA, and then you test
We we've not actively tested temperatures, but we do have a pretty good understanding as a team that's manufactured printed avionics for a long time, what the general sag looks like on different filaments. So TPU and ASA are pretty heat resistant. PLA is the only one that we really have to worry about sag. And so we generally are comfortable flying PLA in school fields since we're in New Jersey and temperatures quite mild. But for this competition in particular, the only choices that were acceptable would have been ASA. Yeah. Yeah.
That is time for questions. So
Thank you all for watching. Thank you. Thank you. So something. Sorry, I'm so sorry.
and dinner. Punch me.
Yeah. We flew ASA last, but because the scary. I'm happy to answer your question too. Okay, thanks a lot. Because the stereos some of the ASA did a really good job there. Ordering vibrations, and chart variations have TP is better down there. I'll be at our table today, so never a destruction.
Thank you so much. Yeah.
No, perché si sta andando qua. Si sta squadra, Fica tu si vuoi una musica da scambiare, prima non è sono gravato. Sì,
So it will be live streamed too, just so you know. I'm waiting for your two judges. I should need blue shirts, so we got about 2.5 weeks before the second start. But they have to be in the room, so I'm trying to find them. But they know when you're gone, so everyone's. Yeah.
Yeah. Because it's like a
Yeah. Oh.
this is a yeah.
I just think yeah, good one. I love
See,
no, yeah. No. What?
Yeah, so your judges aren't here. Feel great, right? You might have to be standing judges.
Okay.
So follow the podium section. They have 20 minutes to present. They do come, I'll send them in. So we start. 5 minutes for Q&A. Good luck.
so we start. Yeah. Well, good morning to everyone. Thank you for coming. We are Cosmic Research, and my colleagues Pablo, Alfred, Sergio, and me are now. We will presenting our volume session about supersonic aerodynamic model validation through our rocket launch at 30,000 feet. First, we will talk a little bit about Cosmic. Our mission is to develop low-cost suborbital rockets for the society benefit, and our vision is to be a global reference for student rocket association. Some basic data about us. We were founded in 2016 in Terrassa, which is very near of Barcelona in Spain. And since then, we have launched more than 40 rockets and more than 100 mini satellites called Cancer. And for the ones that are not in Europe, Cancer is an initiative that the ESA, the European Space Agency, and in conjunction with the schools and institutes of Europe, um, develop mini satellites of the size of a can, and we provide our rockets to launch these satellites to more or less 500 meters, and then they fly in parachute and take some data, pressure, and and also all of this is thanks to our more than 20 sponsors. Here we can see, since our foundation, some of our rockets. In 2016, we can see Valentina, which reached more or less 500 meters. Then in 2017, we made history in Spain, since we launched Resnick, which reached 2 kilometers apogee. And at that time, it was the Student Rocket Association record in Spain. In 2018, we started with the cancer competitions that I have mentioned before. And then in 2019, we started developing our own rocket motors of solid propellant.
However, in 2021, that you can see there, we have to launch Wonder, our first supersonic rocket that we launched it in the unique in INTA, which is a spaceport of Spain. But however, they asked us to validate the rocket with X-rays and a lot of things that was very costly and we needed a lot of time. So we abandoned the idea of developing our own motor rockets and we instead buy a commercial. Then moving to the main matter that we are here, we will do a brief introduction. We will talk about our simulator of flight, babies. We will talk a little bit about the justification of this study, and then we'll talk about the model, the validation of this model, and the conclusions of future work. Okay, introduction. Lucid is our rocket, which is a single stage basically stabilized by four fins. You can see it in our standing at 107, and it is intended to reach an apogee of 30,000 feet. With our past supersonic mission, Bonda, we have the necessity to develop our own simulator and to be able to set our safety areas and know more or less where will be the landing nodes. And since then, we have been improving this simulator. And we would also like to remark that we are the first team in Spain to ever make to the SEA Cup, so we are very lucky and very happy to be here. Okay, moving to Gladys. Gladys is a 6 degrees of freedom flight simulator developed in MATLAB. It's object-oriented, so it is very modular, as you can see here. And on this side, we can see that we have different inputs that we can interchange, and we have different problem cases that we will talk later. We will talk about the standard simulation, which is nominal flight, but we also have stability analysis, Monte Carlo simulation. Later on, we will talk about all of these. Okay, the good thing about our simulator is that we can change the input data easily using different files, and the input data can be differentiated in different categories. We have the geometry data that we can use to calculate things like the center of gravity. Then we have wind data. There is like the wind intensity and direction. Then we have the motor data, that is the curve of thrust that we get from the manufacturer. Then we have the manufacturer data, like the tilt, the position of the platform, and lastly we have Monte Carlo parameters that we use to vary the parameters in order to have different values in our launch. Okay. Now I start explaining the ascent phase of the rocket. It starts in initializing the data from the input data. First, we compute the orientation vectors, and from there we can interpolate time-related data like the thrust, and then we can interpolate data related with position, like the wind direction, and from there we can compute the forces which we will explain later which model we use. Then we compute the accelerations, linear and angular. Then we integrate using branch filter midpoint integration, and lastly we store all the data we previously computed. We do these iterations until we reach the apogee. Then we have the descent phase, where works similar to the previous one, where we initialize the data, interpolate the position, we compute the parachute data when the parachute is open, and the drag coefficients, and then we compute the drag forces, the accelerations, we integrate again using branch filter midpoint integration, and then we store all the data. until we reach the landing. Okay. After making the simulation for ascent descent, we make the post process. Here we can see the rocket trajectory. This information is useful to know how was the flight. Then here we have the graphs for drag force and the normal forces that we use after for making structural analysis. And then we can do Monte Carlo simulators, like I said before. We can vary the nominal parameters, like the tinted angle, the platform elevation or deviation, and thrust misalignment. So we can make sure that for different values of these parameters, our flight is secure. Here we have a picture of one of our flights, Kansas, that we explained before. Here, with using Monte Carlo simulations, we can compute the different landing zones for the rocket, or if the rocket makes a ballistic launching, and we can secure a safety zone. Then we can do the stability analysis. Here we have some graphs that show the stability margin for different angles of attack and Mach numbers, and we use that for dimensionizing our feeds in the first stages of our design of the rocket. And the justification. So why we do this presentation on this project is to validate our model of simulator for supersonic regions. We have seen that Gladys, our simulator, is different in apogee values from other simulators like Open Rocket. So later we will explain how we will validate our model.
So, okay, let's talk about a little bit about the model now. Our model is based on a linear superposition idea in which we divide the rocket into different parts, and we compute the contribution of each part, and then add all them up to obtain the final value of the physical property we are computing. So these expressions we use are basically from Fleeman's and Barrowman's work, under the assumptions of slender body theory and Newtonian impact theory. Also, we account for some interference drag between the fins and the body. For the drag contributions, as I said, we use body, fins, and both tail drag. In this case, we call it base drag. For the body and fins, we consider friction drag and wave drag if applicable. So for the body and base drag, the friction drag we use on the body is only for turbulent flow, as we consider that the rocket speed is so high that it's not necessary to account for laminar flow. Also, the wave drag, the expression for the wave drag is from Fleeman, and there's it's not a lot to say. We just apply the expression. And for the base drag, we have to say that we make a distinction between the subsonic and supersonic regimes, and also between powered and coasting phases of the rocket. Because when the rocket is powered, the laminar flow gets energized by the exhaust of the motor. And when we don't have when MECO happens, we lose this energy and base drag increases. So for the fins drag, similar to the body drag, we use turbulent flow for the friction part, And for the wave drag, we use an approach based on also on Fleemans, which is based on Newtonian impact theory, in which we account for the pressure along the shock waves, along the edge of the leading edge of the peak. For the normal coefficient and the center of pressure contributions, the same as for drag, we use both tail, fins, and body parts contributions, and we compute the center of pressure of the whole rocket as the summation of the local center of pressure of each part, and we compute it as we can compute the center of gravity. The same approach is used here. For body contributions, we use Fleeman's expressions based on gender body theory. Here it's important to say that we don't make a small angle of attack simplification, so we can estimate a little bit what happens if the rocket deviates from the nominal behavior. And also, these expressions are used for all the three flight regimes. So, as you can see here, the center of pressure of the body is similar to the Barman approach. If we consider alpha 0, we recover what Barman is stated. For the fins and normal contributions, for the fins contributions, we have to say here, the important thing here to say is that Fleemans proposes an expression for max above 2, but not in between 0.7 and 2. And similar to what Open Rocket does, we decided to fit a curve, a geometric curve, to try to recover the data we don't have here. Our approach was to make an arc tangent that considers aspect ratio and the Mach number, different to what OpenRocket does, because OpenRocket only considers, if I remember well, only Mach and not aspect ratio considered, and also it's a fifth polynomial fitting. Finally, for the Voltaire contributions, just to say that we use the Barman's equation as they are, there's no change in what we didn't modify. Although this model may be seen complete or likely to be helpful, there are some constraints that we cannot get rid of by now. That, for example, the expressions used for the fins are only for uncovered fins with the root and tip parallel to the flow, only for double wedge or biconvex shapes. On the near future, we want to get rid of these constraints by making more research and try to experiment with more shapes as for the sake of it.
Okay, so to validate the model, we compare the results obtained by Gladys with the data obtained by OpenRocket and real flights. To validate the supersonic model, we've used our low power rocket, Krista, with an apogee of around 1500 feet. This is the rocket that we use in kind of competition. So this runs us around 3 flights per year, which has provided enough data to validate this model. As can be seen in these graphs, the first one, we compare the trajectories obtained by Gladys, Open Rocket, and the real flight. As can be seen, apogees are pretty similar. Maybe the difference here is in descent. The descent times are not exactly the same, but well, when we compare it with real data, both models do fit pretty well. As for velocities, we have similar values in both Gladys and Open Rocket, as well as we have acceleration, so we can say that the sonic model does work pretty well. For the supersonic model, the first idea was to validate this model using the previous supersonic flight we did with Wonder, but when we obtained the data from the launch, we saw that the apogee was significantly lower than we expected. But we don't think this has to do with the model, as there was some factors with the rocket that weren't ideal. And the most significant one is that the fin supports were pretty bulky and were outside the fuselage. So this added a drag contribution that wasn't considered with the simulations. This has been corrected with our new rocket, as the fin supports are now inside, so this will affect. Also actually, also the grains of the motor, the tolerances weren't pretty well. They didn't fit pretty well inside the motor case, so we had to add some pressure, and we suspect this may have caused some fissures that may have reduced the performance of the engine, well, of the motor, sorry. So the idea is to validate the supersonic model using the flight we will do this competition using Rocket Lucid. For this, we will receive the GPS tracker data and barometric values. And with this data, we will receive in real time, so we will know on the site if the simulator works or not. We expect to validate the model.
So finally, to conclude, we have seen that our supersonic model is quite well fitted with the real data. We know that supersonic model may vary when Boulder validation was not effective when validating the supersonic model. So we are counting on this launch to know if our approach for the supersonic model is fine, is okay, and if not, make some changes. And so we have a lot of work ahead. We want in the near future, we want to make a complete CFD analysis of Lucid or other projects we may have, supersonic projects we may have, to modify the expression if needed, and to study a wide range of Mach numbers to know if our expressions or expressions we use fit well with this data. Also, we want to make some more research on the transonic regime because we lack some information on it. And also we want to implement some methods to account for the bulky parts of the rocket that we actually don't have a tool to account for it, especially. And also, hopefully we can test these new supersonic models or iterations of the supersonic model in future Spaceport American apps. Thank you very much, and that's all for us. And this is our score.
I was just wondering, for the integration step, you said you were using the Rush-CUDA midpoint method. Was there any reason behind selecting that specific integration method, or is it just a standard practice that is pretty reliable for integration?
Yeah, we use Rush-CUDA midpoint because it's widely used in different open bracket uses, and I think that other simulators also uses. So instead of experimenting with different integration schemes, we prefer to use the one that everybody does. Okay. So in the future, maybe we can also change it because maybe it also has something to do with the apogee. But at the moment, we use this because everybody does.
Thank you.
Do you compare your data strictly to OpenRocket, or are you considering maybe using other types of simulating software to compare your data to?
Yeah, actually, we would like to compare it with Astos solutions, which is a more like standard simulator. However, with the tight schedule and the development of Lucid, we didn't have enough time because it's more a complex software. It's more intended for more complex rockets and not like for amateur rockets. So, like doing the simplifications needed to do all the inputs of Lucid was very difficult. But yes, we would like to also validate it with Astos, which we suppose it's a more reliable simulator.
Yeah.
A suggestion, particularly for your supersonic flights. I'd like to see comparison against RAS Aero, which I think is a more competent modeling tool particularly for supersonic flight. Years ago, I did a comparison between all the major modeling tools, and rock simulators worse. Open Rocket has gotten very good, but RAS Aero, particularly Supersonic, is really almost right on. I'd be thoughtful against a professional solution like Asterisk as well. That is, there's a contribution we made just comparing those things, right?
Yeah.
Right now we live by word of mouth.
Yeah, moreover, actually, OpenRocket does not have our type of things because we use Lolowets, and OpenRocket has like rectangular plate and like a more like an M shape, and we cannot compare it directly. But however, since it is what we have available now, but yeah, in the future we would like to use a more professional simulator to compare it. Okay, any more questions? Okay, I think that's it. Thank you very much for coming.
They said probably